Welcome. In today's video, we're going to be looking at infinite geometric series. And more importantly, we're going to be looking at what happens to a geometric series as we keep on adding on terms. And is there potentially a limit to the final sum of an infinite sum? So to do this, what we're going to do at the beginning is we're going to consider an example. We're going to consider an example of a geometric sequence where we begin with a, or a equals 1, and we're going to have a common ratio of a half. In other words, we go from 1 to a half, to a quarter, to an eighth, to a 16th, and so on and so forth. Each successive term we divide by 2. Now, the corresponding geometric series will therefore be something like 1, 3 over 2, which is given by the sum of 1 and a half. Next term in the sequence is 7 on 4, which is given by the sum of the first 3 terms here, 1, a half, and a quarter. Then the 15 on 8 in the geometric series is 1, a half, and an eighth, and then so on and so forth, and we can continue onwards. However, in general, what we could say is that the nth term of the geometric series, again, we're going to use our formula that we've derived before, which looks something like this. Usually there's a 1 minus r to the n over 1 minus r. But in this case, our a, remember, is equal to 1, and our r is equal to a half, so we're replacing this r here with a half. We're going to do some simplification here in the denominator. 1 minus a half just becomes a half in the denominator. And of course, now we can re-express this as 1, or we can separate the numerator as 1 over a half, which gives us actually 2, and we have a half to the power of n, which divided by a half becomes a half to the power of n minus 1. Now, our goal here might be to discover what happens as n approaches infinity, and this is the idea of an infinite geometric series. What happens as we keep on adding terms to the sequence? What is the ultimate behavior of the sequence, or sorry, of the series? And we're going to explore that through the idea of limits. So, we could say that the infinitieth term, or as n approaches infinity, really, we say that the sequence, or sorry, the series approaches this limit, this idea of as n tends to infinity, we want to know what Sn goes towards. And I'm going to replace Sn here with our expression that we derived on the previous page as 2 minus a half to the power of n minus 1. Now, of course, as n approaches infinity, or as n gets bigger and bigger and bigger, it doesn't really affect the 2. The 2 doesn't change depending on infinity. So we can actually use one of the limit laws and say that this is just 2 minus, well, the limit as n approaches infinity of this second term here. We're only really interested, only the limit as n changes, it only really changes that second term. And now we've got to ask ourselves, what happens as n approaches infinity of this second term here? And, well, think about it here. We've got a half to the power of n minus 1. When n equals 1, what did we have? We had a half to the power of 0, which is 1. When n equals 2, we have a half to the power of 2 minus 1, so a half to the power of 1, we get a half. When n equals 3, we get 3 minus 1, so that's 2 at the top in the power, so a half to the power of 2, which gives us a quarter. In other words, we go from 1 to a half, to a quarter, to an eighth, to a 16th, and so on and so forth. In fact, that number keeps on halving and halving and halving and halving and halving again. And eventually, well, it approaches 0. Because if you keep on halving the number and halving the number and halving the number, you get so small, you approach 0. And so in fact, this limit here, it just becomes 2 minus 0, which is 2. So in other words, what we've shown is that if you add a 1 plus a half plus a quarter plus an eighth plus a 16th, the idea is that it converges, or this sum converges to 2. So I want to explore this visually, actually, now. So again, remember that the nth term in the sequence was a half to the n minus 1, and the nth term in the series was 2 minus a half to the n minus 1. So after one iteration, or after one summation here, we have that we've added 1, so that's the first term in the sequence, and that gives us the first term in the series, which is 1. Then we go to the next term in the series. The next term in the series is 3 on 2. That's after we add in a half. And then we add in another quarter to the series, another quarter to this series, which gives us 7 on 2. And what you notice going from this part to the next part, let's just observe what's happening here. Originally, we have a distance of 1 from 2. Then after we add a second term, we're a distance of a half away from 2. Then we're a distance of a quarter away from 2. So you notice that each time we add a term in the series, we keep on halving the distance between the current term in the series and 2. And so eventually, by halving that difference each time, we actually get to 2 eventually, or in the limit. I should be more specific with my language. So that's a very specific example. Let's just discuss what happens in general when we have an R and an A instead. So in general, remember that the sum of the first n terms of a geometric series are given by a times 1 minus r to the n over 1 minus r. Now, provided that the absolute value of r is less than 1, and remember in this particular instance, remember r was equal to a half, and so the absolute value of a half is definitely less than 1, then the series is convergent. In other words, this part here in the numerator, as we'll see, the r to the n actually diminishes. It gets smaller and smaller and smaller. Remember, a half to the n gets smaller and smaller and smaller. If you do not have this property of diminishing power, so for example, if we have r is equal to 2 at the top, we've got 2 to the power of n. That continues to increase. So it goes 2, 4, 8, 16. It does not diminish. So we need this property of diminishing power. So then we can say the series is convergent. And so let's have a look at exactly what that series converges to. So again, we've got that the series converges to S or Sn as n tends to infinity, or S infinity. It converges to S infinity, or that's my label, which is the limit as n tends to infinity of Sn. So then again, we can write this as the limit as n tends to infinity of a 1 minus r to the n over 1 minus r. Now again, the a, remember a, 1, and the 1 minus r do not depend on this value of n. And so we can actually write this, or firstly, the a definitely doesn't depend on n, and so we can actually say, we can bring the a out the front, so that becomes a times the limit using our limit laws. And then of course we can rewrite this, put this limit in the actual numerator here at the top, limit as n tends to infinity of r to the n, again because that limit does not influence the denominator, nor does it influence the 1, it only influences the r to the n. And of course, when we have this fundamental property that the absolute value of r is less than 1, then this power r to the n diminishes, or it goes towards 0, and so we're left with a times 1 minus 0 over 1 minus r which nicely simplifies down to a over 1 minus r. And so this is in fact the general sum of an infinite series. Or sorry, this is the general infinity, or the approaching, what an infinite series approaches, given that the absolute value of r is less than 1. Now, let's go through an example, a more concrete example, to explain what's happening here. So, suppose that a ball is dropped from a height of 20 meters, as shown in the diagram below, and on each bounce, the ball bounces 3/4 of the height of the previous bounce. So here you'll see that it begins at a height of 20 meters, it drops down to the bottom here, down to the bottom, then it bounces back up to 15 meters, of course, because it bounces back up to 15 meters, that's 3/4 of 20. Then it would bounce back down, or sorry, then it would head back down due to the gravitational pull of the Earth, and then bounce back up, but only bounce back up 11.25 meters, and 11.25 meters is 3/4 of 15. Then bounce, and then again head down to the ground, and then bounce back up and give me 8.4375 meters, and so on and so forth. And it keeps bouncing and bouncing and bouncing. Now, theoretically, the ball never stops bouncing. Again, because although the height halves each time, technically there's always a half height in between. But we want to find the total distance traveled by the ball before it comes to a rest. Well, does it really come to a rest? That's a very much a dispute between the theoretical mathematicians and the physicists. Theoretically or mathematically, no, it doesn't come to a rest because it keeps on bouncing, even if those bounces cannot be observed. Even if they're atomic, even if we get to the level of the atom, theoretically those bounces are still occurring mathematically. But for the time being, we're going to assume comes to a rest is interpreted to mean the limit of that distance. In other words, here we're kind of summing successive terms of a geometric series, or a geometric sequence, I should say. So we're really interested in that limit. That's what it means to be at a rest. So, let's have a look. How would we do this? Well, the total distance traveled by the ball is, again, the first 20 meters. And here we've got the 20 times 3 on 4, which is our 15 meters that I was talking about before. But we're actually multiplying by 2 here. And why did I multiply by 2? Because remember, the ball has to go first bounce up to 15, and then it has to bounce down to 15, which means you've got 2 lots of 15 happening here. And equally, if we go again, we've got 2 lots of 20 times 3 on 4 squared. So the 20 times 3 on 4 squared, just having a look here, is the 11.25 meters. But again, we have to multiply by 2 because it goes up and down. Again, by 2 goes up and down. So then from here, and of course this process continues on for infinity theoretically. Then of course what I'm going to do is I'm going to rewrite the 20 times 2, all these 20 times 2's, all these 20 times 2's as 40's. And you'll notice now something here, that this part of the summation, 40 times 3 on 4 plus 40 times 3 on 4 squared plus 40 times ... that very much looks like the sum of a geometric sequence. The only difference is, ideally we'd want a 40 at the beginning, right? A 40, because this is A and this is our R. We'd want a 40 at the beginning here. We only have a 20, so what I'm going to do strategically, again, is I'm going to add a 40 in, because now this looks exactly like the sum of a geometric sequence. But I'm going to subtract 20 so that, again, overall this negative 20 plus 40 gives me back the original 20. But now I can rewrite this infinite sum here, again using our notation, because R in this case is 3 and 4, and that absolute value of 3 and 4 is less than 1. I can use our formula A on 1 minus R, or in other words 40 on 1 minus 3/4, I've still got this negative 20 at the front, and after some simplification, some arithmetic, we arrive at our answer to be 140. Okay. One last example for the day. We're going to look at the fractional representation of a few decimals. Something that now we're going to kind of prove a few results here. So we're going to look at the recurring decimal 0.7777, the recurring decimal 0.09090909, and so on. And we're going to also look at the repeating decimal 0.99999 recurring. And what we're going to do is we're going to come up with a fractional representation of each using this idea of an infinite series. So let's do that. So we can rewrite the fractional representation of 0.777 recurring as 0.7 plus 0.07 plus 0.007, and so on and so forth. And then what we can do is we can rewrite this 0.07 as 0.7 times 0.1. We can rewrite the 0.007 as 0.7 times 0.1 squared, and so on and so forth for each successive term afterwards. And you'll notice now that this is exactly a geometric, or the sum of a geometric sequence, or a sum of an infinite geometric sequence. And now we can use that A is equal to 0.7, and our R is equal to 0.1. And of course that absolute value is less than 1, so we can make use of the formula A over 1 minus R, which gives us 0.7 over 1 minus 0.1, which comes out to be nicely as a fraction 7 on 9. Let's do that again for the decimal 0.090909 recurring. So now we can write 0.090909 recurring as 0.09 plus 0.0009 plus 0.00009, and so on and so forth. So again, each successive time we jump, you see that we've got 2 extra zeros. So from here, we've got 1 0, now we've got 3 zeros, so we've got 2 extra zeros. 2 extra zeros become 4 zeros, and so on and so forth. And therefore, we can actually write in the next term, or the next equation, or the next line of the equation, we can replace 0.0009 as 0.09 times 0.01. Remember, multiplying by 0.01 adds 2 extra zeros in the decimal representation. And again, we can do the same for the next part, or the next term in the sequence. Again, we're adding now an extra 4 zeros to 0.09, and that gives us, essentially we're multiplying by 0.01 squared, and so on and so forth. Again, you'll notice that this looks like a geometric sequence, so we're going to use again the property that our R value, which in this case is 0.01, has an absolute value less than 1. So we can now rewrite this as 0.09 over 1 minus 0.001, which actually turns out to be 1 over 11. And finally today, we're going to look at a very mysterious property that you might surprise you in this case. We're going to be looking at the repeating decimal 0.9999 forever. So again, we can rewrite 0.9999 recurring as 0.9 plus 0.09 plus 0.009. And again, in the same way we dealt with the 0.7 recurring, we can write this as 0.9 plus 0.9 times 0.1 plus 0.9 times 0.1 squared. And again, it's a geometric sequence, so we can rewrite this as 0.9 over 1 minus 0.1, again with our r being 0.1 and our r being, sorry, an a being 0.9 and our r being 0.1, which of course has an absolute value less than 1. So we can make use of this term. But what's interesting is that this is equal to 1, which is kind of a mysterious part of mathematics and one that I quite like. So the next time someone tells you what is 0.99 recurring, you can tell them it's equal to 1. As funny as that does sound, it is true. And that's where we'll end the video for today.